Okay, so I fixed this last slide, and this is what you have in your version of the slides. So from the previous slide, we calculated the distance between BC and AD. The two clusters BC and AD, we found 6.75. So here this height is half of this, so it's 3.375. And that's why here you have 2.375 and here 1.875. Right, so the UPGMA is an automatic technique for tree inference that works based on matrix of pairwise distances between taxa. And this method creates a rooted tree, and this rooted tree has certain properties we're going to see in a very short amount of time, in 2 slides from now. So be careful. In UPGMA, we use arithmetic averages, but these are weighted averages. So remember, in the definition of the algorithm, we had it that the distance between 2 clusters is the average distance between pairs ij of taxa with I in one cluster and j in the other. Okay? So if there are 3, for instance, if there are 3 taxa in one cluster and 2 taxa in another, you'll have to average all the distances, the 6 distances involving pairs of taxa, one being in one taxa in one cluster and the other being in the other cluster. For instance, in the preparation of cluster ABC, imagine you already know clusters A, B, and C. You already have built clusters A, B, and C. The distance between A, B, C, and E, the new cluster A, B, C, and taxon E, will be made of 2/3 of the distance from A, B to E, and 1/3 of the distance from C to E. Okay, so there are weights corresponding to the relative abundance of taxa into this group AB versus this group C. Okay, here you have 2 taxa, here you have only 1 taxa. So be careful when you are building by hand UPGMA tree. The most common error is to forget about the weighting of the averages, and the error would lead into saying the distance between A, B, C, and E is half of the distance between A, B, and E, plus half of the distance between C and E, which is wrong. Properties of the UPGMA tree inference. The trees reconstructed by UPGMA are ultrametric by construction. Okay, they are rooted trees, and there is the same length for the path from the root to any leaf. So this is an example of an ultrametric tree. The distance between the root to D is the same as the distance between the root to A. Okay. The distance between the root and any of the leaf is the height of the root as defined by the UPGMA algorithm. This tree is non-ultrametric, meaning that you have a shorter distance between the root and A. The distance is shortened than the distance between the root and D, for instance. And remember, the distance in a tree must be proportional to the expected number of mutations. So since all sequences corresponding to the taxa, or all traits measured corresponding to the taxa, are extant traits, we're always working with current data. Either we have 2 possibilities. Either this tree is wrong, it doesn't correspond to the reality of what happened biologically to the 4 taxa, evolutionarily speaking, or the molecular clock doesn't hold. The molecular clock hypothesis says that the mutation rate is constant all across the whole tree. So maybe the molecular clock hypothesis does not hold, and there has been a slower divergence from the root to A than from the root to D. Okay, this path accumulated more mutations in the same amount of time, of geological time, than the path from this point to that point. So, but if the molecular clock hypothesis holds, then UPGMA reconstructs the true tree. That's a statement based on the assumption that we would know the true tree. And that's not always the case. That's a theoretical assumption about a theoretical statement, about the UPGMA method. We see that if it's the UPGMA is put at work on a matrix of distances inferred from a true tree where the molecular clock hypothesis holds, then UPGMA reconstructs that true tree. Now, additivity is another property. It's not exactly this definition. Additivity of the distances. So if in case the distance between any pair of leaves is equal to the length of the path between them, the tree is said to be additive. A set of distances is additive if it abides by a certain condition that is called the 4-point condition. And this 4-point condition is a stronger version of the triangle inequality. So UPGMA always yields an additive tree, but the final distances do not always equal the original distances from the distance matrix. So we can see it in this example. For instance, here we see that the final patristic distance given this tree between A and D is 3, and that's what was expected. But the patristic distance in terms of length of the path in this tree between A and C, for instance, is equal to 6.75, right? Because the height here is 3.375, so going from A to C, if you sum this distance, this, and this, the 4 branch length, the sum is equal to 6.75. That's the distance observed in this tree between A and C. And if you go back to the original matrix between A and C, we had an original true distance of 7, right? So it's not what we have at the end. And the error is even bigger between A and B. The original distance was 9 from the true distance is 9 from the distance matrix, and what you have here from A and B, from A to B or between A and B, is also 6.75 distance. Okay, so you see we don't respect the original distances, not all of them. So if additivity holds, so if the tree, if the original matrix abides, if all the distances in the original matrix abide by this 4-point condition, but if trimetricity does not hold, then UPGMA will not reconstruct the correct tree, and that's a drawback of the UPGMA, a disadvantage of the UPGMA tree inference. Because we know that the molecular clock hypothesis is not true. Some branches of the tree of life have evolved at a faster rate than others. So it's important to be able to design tree inference methods that do build the correct tree in case the ultrametricity property doesn't hold. So way after 1958 and the advent of UPGMA, Saitu and Ney in 1987, and Studer and Kepler in 1988, developed a method that always reconstructs the correct tree if the set of distances is additive. And this technique is the neighbor joining algorithm. It's more popular nowadays than UPGMA, but UPGMA is more simple to show as a first algorithm of distance matrix-based tree inference. So NJ is more complex, and it uses corrected or modified distances calculated in a certain way from the original distance matrix. It's the most popular distance method now, and it's used still nowadays to build guide trees for multiple sequence alignment algorithms. You've had a module on multiple sequence alignment, and part of this IBT course, and you must know that most methods of multiple sequence alignment are progressive. methods of alignment. So they build a progressive model and they align this model to new sequences, or they align new sequences to this model gradually, while they are going along the branches of a guide tree. So the guide tree is something that is must be built relatively quickly at the beginning of of the process of multiple sequence alignment. And to build this guide tree, many multiple sequence aligners use the NJ algorithm or a refinement thereof to get this guide tree. One of the refined implementations is BioNJ. NJ established by Olivier Gasquel in 1997. Sorry. So just a summary on distance methods. We have two main algorithms, UPGMA and NJ. These methods are suitable for a wide range of data, and that's their strongest advantage over other techniques, because you only need pairwise distances between taxa and then you're good to go. So it's distances can be established on various kind of objects. You can imagine to have distances between pieces of texts and establish phylogenies between books, or to have distances between societies, distances between groups of friends on a social network, etc., etc. These algorithms are fast. You've seen that the UPGMA algorithm is quite fast. I mean, it's quite straightforward, so implementations on a computer will be fast. It's n-1 internal nodes created one by one, so you have a linear complexity always. Because in a phylogeny with n taxa, you have n-1 internal nodes. And since these methods are greedy, as I said, we don't go back to cancel something that we've already done, or a cluster that we've already built. So this greediness makes it that all these algorithms have linear complexity, which is a great advantage. And we have no costly exploration of the set of all tree topologies. These algorithms are greedy. They don't go back. They don't cancel what they've done. They don't say, oh, I've made a mistake, or maybe I would get a better tree doing this or that, modifying this tree in a certain way. No, we never do this in UPGMA and NJ algorithms. So there's no costly exploration of the set of all tree topologies, so that's why they're fast. Now, routing the tree. UPGMA yields rooted trees. NJ and other methods that we'll see later produce unrooted trees. So now, placing a root is interesting because it gives an idea of how the time flew through the branches of our phylogeny. Okay, if you don't know where your root is, if you are inside an unrooted phylogeny, when you look at a branch, you don't know whether time was evolving from one node to the other, or from that other to the first. Okay, so placing a root in a tree gives you the arrow of time, in a way, on all the branches of your phylogenies. So, in case the molecular clock property holds, in case the rate of evolution was the same throughout, then one can choose for the root the midpoint on the longest path between any two leaves. Okay. By the way, it's good for you to know that this longest path between any two leaves defines what we call the diameter of the tree. Okay. When you have an unrooted tree, you cannot talk about the height of the tree because you don't know where the root is, but you can always talk about the diameter of a tree, and by definition, the diameter is the longest path. Take the two leaves that are the furthest from each other, and you have, with their distance, you have the diameter of of the tree. So this diameter defines a path, or this path defines the diameter, and take the midpoint on this path, then you have a potential root, and that's the correct root in case the molecular clock property holds, in case the rate of evolution was constant all over the tree. Otherwise, another very common technique is the technique of the outgroup, and it's extremely simple. An outgroup is an extra taxon that you add. It's not a taxon that belongs to the set you want to study. It's another one, and this one must be outside of your set of species, outside of the clade defined by the set of species you're studying, or the set of taxa you're studying. Okay, so it must be his most recent common ancestor with any taxon in the tree must predate the MRCA of any two taxa in your existing group of taxa under study. So, for instance, if you want to study if you want to study mammals, for instance, you're going to take as an outgroup, if your phylogeny is made only of mammals, you're going to choose as your outgroup an animal that is not mammalian, okay? And then, after you've built your phylogeny on the set of taxa of interest, use this extra taxa, aggregate it to your data, and build automatically your tree, including this new taxa. And the purpose of including this new taxa is just to know where does it branch with the rest of the tree. And this point where it branches with the rest of the tree is the point you're going to choose as your inferred root. Okay, and it does make sense because you've chosen this taxon, as a taxon that you know is outside of the group of interests. So necessarily where it branches on the tree is a moment that predates all the common ancestors of belonging to sets of taxa within your set of taxa of interest. So that's the technique of the outgroup. Just use artificially another taxon that you know is evolutionarily distant from this group, and see where it connects with the rest of the tree. And this technique of the outgroup can be used whatever tree inference method you're using, right? We can use this also in maximum likelihood phylogenies or in minimum evolution phylogenies, etc. Okay, let's have a break now.